All right. So let's remember what we talked about last time. We talked about P and NP. That's NP. Search problems. What is a search problem? What is a search problem? Search problem, you are given an input and you want a solution. Or an answer that says, sorry, there is no solution. And the point is, important thing to remember about search problem, that there is a test whether this is indeed a solution to this input. Okay? And the test runs in polynomial time. Okay? That's what makes a problem a real search problem. For every input, you want to find a solution. There may be many solutions. You want one of them. Or there could be no solution, in which case you want the algorithm to tell you. And what makes a problem a legitimate search problem is the fact that there is an algorithm that tests whether the solution is indeed a legitimate solution for the input. And this test, of course, should be done very fast. And we have many examples, like satisfiability, 3SAT. Given a Boolean formula with many clauses, can you find me a truth assignment that satisfies it? Or tell me no such thing exists. And if you give me a truth assignment, I can test whether this truth assignment indeed satisfies each and every clause of this Boolean formula. So what else? Then what is then we talked about reductions. What does it mean to reduce a problem A to a problem B, a search problem A to a search problem B? And basically, it means to find a way to solve A using any algorithm for B. Okay, that's what it is. It is a demonstration that if you give me any algorithm for B, I will be able to solve problem A. And we said that this is the same as saying that A is no harder than B. Okay? Since you can reduce A to B, then this means that A is no harder than B. All right? Always remember that. As we said, there are many ways to use the reductions. You can reduce A to B, and B is in P. In other words, it can be solved in polynomial time. You see, this is NP, this is P, and this is NP complete. If you can reduce A to B and B is in P, what have you proved? A is less than or equal to B, B is in P, of course, A is in P. Okay? You can reduce A from NB. For A is NP complete, and we have reduced it to B. What have you proved? Everybody sees that? You have proved that B is NP complete, because what is NP complete? Means two things. It is a search problem in NP. In NP means it's a search problem. It's a legitimate search problem. This is the world's easiest way to lose 1 point in the final, okay? Because we are going to tell you, prove that the problem is NP complete. And people forget to say, okay, I have to prove that it's NP, because it's always trivial, okay? Of course it's in NP, okay? So remember that. Always, when somebody tells you, prove that this problem is NP complete, first thing you say, of course it's NP, it is in NP, blah, 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 okay? Usually the reason is trivial, okay? Because if you give me a solution, of course I'll be able to tell you it's a solution. In NP and all other problems in NP B reduces to A. All other problems in NP reduce to it. Okay, it has this amazing property that, it's NP complete. It is the hardest problem in NP. Every other problem in NP reduces to it. Okay? So, these are two things that you can do. Imagine that you reduce A to B, and B is NP complete. What have you proved? No. You prove that you don't know what you are doing, okay? You see them? You see my point? Right? B is in NP complete. Of course A reduces to it. We knew that. Okay, you get the point? Yeah. It is in NP. Yeah, but suppose you knew that. I mean, you use it, yeah. Exactly, exactly. Yeah, yeah. This means that you were wrong and the A was not NP complete. Yeah. Yeah, excellent. Or you prove that P equals NP and you are rich and famous. Okay, right? I mean, listen. Okay, I know it sounds like a joke, but it's serious. It's a mathematical possibility. I wait. Every day I wait that. I'm expecting that tomorrow I'll wake up and a kid has proven that P equals NP. Okay, or that P is not equal to NP, all right? So that's, all right? So what I'm saying, because a problem is difficult, it doesn't mean you shouldn't work on it, okay? But here is the point, okay? I'm not here to discourage you to work on P equals NP. But if somebody gives you an NP complete problem to solve, and you don't know that it's NP complete, you know what you are doing? You are doing something bad, okay? You are working on P equals NP without knowing that you are working on P equals NP. You see my point? So that's why there is value in recognizing NP complete problems, okay? There is value of having developed the cognitive tools necessary to say, wait a minute, are you kidding me? This problem is NP complete, okay? And throw it back at the face of your boss, okay? All right? All right, so you can see these lectures as a quick tutorial about these skills, okay? How to prove a problem, to recognize NP complete problems. And we're going to do all these reductions, okay? So let's start easy. Let's start with this reduction, which is the easiest of all. And basically, it's going to tell us what, so here is, what is Rudrata cycle? Okay, Rudrata cycle is you are given a graph. Okay, and you are asked, is there a way to visit all the nodes in the graph without visiting anyone twice, right? That's what the Rudrata cycle is. That's what this problem is. Everybody with me? What do you think the answer is here? Yes. I'll trace it for you. Oops. Right? I can do it. Yeah, believe me. Yeah. Okay? What is Rudrata path? Rudrata path is trickier. You are given two nodes, S and T, and you are asking, is there a way to do this with a path going from S to T? Okay? And again, you can do it, I think, okay? You go from here, there, then all the way around. Okay? And intuitively, it's very clear that Rudrata path and Rudrata cycle are the same problem, okay? Right? And what we're going to show is that Rudrata path reduces to Rudrata cycle. In other words, they are giving us this graph, okay? And they are giving us a routine, a program that solves Rudrata cycle, okay? And we want to solve Rudrata path. How would you do it? Okay? How would you modify this graph so that, I want you to think about it. How would you modify this graph so that if the program you have for Rudrata cycle gives you a cycle, you will be able to recover from the cycle a path. If the program tells you none, I couldn't find one, you should be able to be confident that there is no Rudrata path from S to T here. Okay? So, you want to find a simple way to modify the graph. Is everybody feels the problem, what we want to do? That's what a reduction is, okay? We want to modify this graph so that the resulting graph, if we submit it to the program as an input to the program that gives you, that answers the Rudrata cycle problem, should be able to give you an answer to the Rudrata path. If it gives you a cycle, you should be able to modify the cycle and find a path from S to T that goes through every vertex. If it tells you no, you should be confident that there is no such path. Yeah? Okay, so you are halfway to what you have to do, but it's almost that. Okay, that would solve the problem. Is there a Rudrata path from S? But it does nothing about T. Okay, so yeah, okay. So, but everybody understands the problem. What we want to do, and I'll do it in front of your eyes. Okay, so here is the answer. Here's what you do. You create a new node and do this. Get it? If now you have a cycle, this cycle must, when it comes here, it must have come from here and going there, okay? Or from here going there. So if you take out this, you have a Rudrata path from S to T. And if it tells you, no, there is no such path, such cycle, you know that there is no such path. Because if there was a path, there would be a cycle. And if there was a cycle, there would be a path. So basically what you do is that you have to prove that there is a Rudrata path in the old graph, even if there is a Rudrata cycle in the new one. That's what you have to prove. And then you are done. You are off the hook. It means exactly that you can use any program that solves Rudrata cycle to solve Rudrata path. Everybody understands this. Okay? Listen, I'm starting with the easiest of these reductions because I want you to see it very clearly, okay? And then see how you can, in more complicated situations, come up with other reductions like that. Any questions? So as I told you, today, weather permitting, we are going to do all these reductions, okay? And of course, we'll leave for last the most interesting reduction of all, which says that any problem in MP reduces to satisfiability, okay? In other words, that this cycle is closed, okay? In other words, all of these problems reduce to satisfiability. All right? So this thing is a mess, okay? It's a doubly connected graph. Strongly connected directed graph. All these problems are equivalent, okay? You know, here is the amazing thing, that you look at these problems, they look so different, and yet they're the same problem in disguise. Okay? And your job now in these 2-3 lectures is to get the skills to reveal the disguise, okay? To expose the disguise. Say, wait a minute, this is satisfiability. Are you kidding me? All right? So this is our goal. Okay. Any problem? Any questions? All right. So let's, after this, everybody understood this? Ask a question, please. How? Okay. So we want to reduce Rudrata path to Rudrata cycle. Rudrata path is this problem, okay? You are given a graph and 2 nodes, and you want to find a cycle, a path that goes through all the nodes, from S to T. Rudrata cycle is you want to find a cycle. We want to reduce Rudrata path to Rudrata cycle. In other words, given any program that solves Rudrata cycle, we want to show how to use the same program to solve the Rudrata path. And the way is simple. We add a new node and edges to S and T. And now it's crystal clear, it should be pristinely clear that there is a Rudrata path in the old graph, even only if there is a Rudrata cycle in the new one. Okay? Because if there was a Rudrata path in the old path, then with these 2 nodes, that's a Rudrata cycle in the new one. And if there is a Rudrata cycle in the new graph, then this Rudrata cycle will go through this node this way, because this node has degree 2. In a Rudrata cycle, it has to go from here to there, or from here to there. No matter how it goes, it's going to essentially prove to us that there was a Rudrata path in the original graph. Yeah. No. Rudrata path means that there is a path from S to T that goes through every single node of the graph. For Rudrata cycle, it means that there is a cycle that goes through every node of the graph. If there is a cycle, what I claim is that it will have to go from S to this to T. There is no other way. How would you draw a cycle in this graph? How would you pick up this node? This node has to be picked up. Yes? No. No. Okay. Hello? Okay. Okay? Questions? All right. What next? So let's do this one. Everybody remembers what independent set is? Let's take this graph, okay? It's the world's simplest non-trivial graph, so so let's use this graph. What is independent set? Everybody remembers? Find as many nodes as you can, as long as they are not connected. What is the independent set of this graph? The independent set number. What is the maximum number of nodes you can find that are not connected? Everybody believes that? 2? Is 2 clear? Okay? What is the clique of a graph? Do you know? The clique number of a graph. Anybody knows? Clique number of a graph is basically the opposite of independent set. It means I want to find as many nodes as I can and should be connected in all possible ways. Okay? In other words, in a social network, I want to find the largest number of people who are all friends between them. So imagine that this is a social network. How many people can you find that are all friends between them? 3. Okay, so independent set number is 3, and clique is, 2 and 3. Everybody with me? What are the 3? Either these 3 or these 3. Right? Any triangle would do. It has 2 triangles. How about vertex cover? What's the vertex cover of a graph? It is the, right, you remember. So it's the smallest, you remember the, you are trying to forget, I know, but you remember, so the painful problem, right? I mean, you want to find nodes that do what? That together cover all edges, okay? What is the smallest number of nodes you can find in this graph that together cover all edges? What is the answer here? Everybody sees that? Ask questions. Okay? 2. Sorry? That every edge is adjacent to one of these 2 nodes. Okay? So if you put guards on these 2 nodes, you are controlling all edges. If you place guards on these 2 nodes, you are on these 2 islands, you control all bridges. Right. So these 2, right? These 2 would be enough. So the answer is 2 here. Everybody sees that? Actually, do you notice anything? It's the same or something else? It's n minus 2. Yes, exactly, yeah. Get it? A vertex cover. Visualize a vertex cover. What are the other nodes? They are an independent set, because if they were not independent set, if they had an edge between them, then this edge would not be covered. So always, the vertex cover is independent set, okay? N minus independent set. Okay, you just subtract n from the, everybody sees that? Okay. Here's the point, that if S is a vertex cover, V minus S is an independent set. Why? Because if these 2 guys are a vertex cover, then these other 2 guys must be independent, because if they were not independent, if there was an edge between them, then this edge would not be covered, and this would not have been a vertex cover. Get it? Okay? Yeah. Sorry? The what? Clique. Something else. Okay, we'll talk about it in 30 seconds. Yeah. No. No. Hey, sorry. It's a special case of the set cover. It's a special case of set cover, where the elements are edges and the sets are vertices. Okay? Think about it. Good observation. Yeah. So it's right. Clique. What is clique? Clique is a bunch of nodes, all of them connected, all possible ways. Okay? Somebody had asked. Somebody had asked about clique. Yeah. All right? You see why it's 3. So there is also a very interesting relationship between independent set and clique. Anybody sees it? Right. So here is what you do. All right? So, so here's what you do. To go from independent set to vertex cover, you subtract from n. To go from independent set to clique, what do? Here's what you do. You draw a new graph, and then you draw the edges that are missing from this graph. Okay? So, this is the only edge that is missing from this graph, okay? What is this clique number of this graph? What is the maximum number of friends you can find that are friends between them? 2. Get it? Okay, because if they're independent in one, they must be clique in the other. Because missing edges here, existing edges there. Okay, so, all right? So the point is that these reductions are easy. Basically, what you do, you go from G and K for independent set, you go to G bar and K to get to clique. In other words, you reverse the edges of the graph and you keep the same number. That's what we did. From here, this and 2, we went to this and 2. And to go from here, you keep the same graph and you do n minus k. Okay? So you see what I'm saying, that these problems are clumsy disguises of one another? They're really the same problem. Okay? Different people look at them for different ways, but really it's one problem. All right? If you know how to solve one, you know how to solve all. And more to the point, if you don't know how to solve one, you don't know how to solve all. Right? Everybody got that? Yeah. Let's see how. The best vertex cover means the smallest vertex cover. The best independent set means the largest independent set. Since one is n minus k and the other is k, maximizing k is the same as minimizing n minus k, right? Is it clear? The smallest will be largest. Yeah, good question. Yeah. This one? That's G bar, yes. If this is G, this is G bar. Why? Because this edge is here. 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 That's the only edge missing. No, that's the clique of G. Right? What I'm promising you is that the clique of G bar is going to be the same as the independent set of G. Okay? Good, thanks. I mean, I'm sure it confused others also, okay? So, the clique of G is 3, but the clique of G bar is 2. The independent set of G is 2, and therefore the clique of G bar is 3. Yeah. Yes, right, yeah. For the reason we said, right? I mean, that the vertices have to be, yeah. There was another question? Of G. Yes, exactly, yeah. So good point. That these are so easy reductions that you can go back also, right? Yeah. I mean, these are almost no reductions, right? I mean, they are just notational translations, right? I mean, it's just You know, if you think about it, it's minimal what you have to do to carry out these transformations. Okay, go forward. You want to see a real reduction, a real like hardcore red-blooded reduction? Okay, so these were like, yeah. Hardly worth the name, okay? So let's do a real reduction. And here's what we're going to do. We're going to see this one. How you go from 3-sat to independent set, okay? Here is why it's difficult, all right? Because we saw how do you go from Rudrata path to Rudrata cycle. Big deal, okay? So, you know, it's a path problem in a graph, a cycle problem in a graph, of course, okay? I'll think about it, I'll do it in there. Here we went from one graph problem to the other, okay? Click to independent set to click, independent set to vertex cover. Graph problems, closely related, easy, all right? Here we have to do work, okay? Because you want to go from a problem in Boolean logic to a problem in graphs, okay? And that's actually quite common, okay? Because 3-sat is a convenient place to start reductions, all right? And so often in your NP completeness reduction career, you are going to be reducing from 3-sat, okay? And doing this, going from 3-sat to another problem, essentially what you have to do to a problem in graphs, let's say, like the independent set, you have to translate logic into the language of graphs. Okay, that's challenging. Okay, it's not for the faint-hearted. Okay, all right. So how do you do it? How do you translate the language of logic? So let's see. Okay, and to give you a short answer, basically what you do in all of this, you know, we also see it here for tripartite matching, which is a really fun reduction. What you have to do is you have to create graph theory, little graphs, okay, that encode the properties of logical variables and clauses, okay? That's, and so these are called gadgets, okay? That's in NP completeness lore, okay? And so you have to come up with gadgets, okay, that really capture the idea of logic into graphs, all right? So let's see how to do that. So we're going to go from 3-sat to independent set. Everybody with me, okay? Please pay attention, okay? Because this is our first really hardcore result, all right? So let's see. Imagine that you have a 3-sat formula. So that's not fun, right? So I should do something. Okay. Okay. First of all, what do you think? Is it satisfiable or not? Not so easy. I think 0, 1, 1 does it. What do you think? Satisfies the first, satisfies the second, satisfies the third, satisfies the fourth. Oops, no. Doesn't satisfy the fourth. Okay. 1, 0, 1. It did? Oh, yes, yes. No, why? Oh, okay, sorry. Yes, I thought it was Y and Z. Okay, sorry, sure, okay. All right. I'm better than I thought. Okay, good. Yeah, so, all right. So let's see how to transform this into, you see the challenge, okay? It should be knee-weakening challenge, all right? I mean, you want to translate this Boolean formula, this set of variables and clauses, into graphs, okay? And you want whether these graphs to tell you if or not this graph to tell you whether or not this formula is satisfiable, okay? By solving the problem in the graph, you should be able to come up with this, okay? Here's how it's done, okay? So, for every clause, you have a gadget. This time, the gadget is simple, okay? The gadget is just a triangle. 3 nodes, 3 edges. Triangle, 3 sat, get it? Okay, that's, all right, so, a triangle for every clause. And of course, this guy who has just 2, we give him 2. And what? Now, each one of these guys is all right? Why do I insist on these triangles and this line which corresponds to the 2 clause? Here is why. Because what I want to do is what is the property? Now, remember, here it's logic. Down here is graph theory, is the domain of the independent set problem. And let's take the triangle. What do I know about the independent set of a triangle? What is the independent set of a triangle? Everybody sees that. If I have a triangle, the independent set is 1, okay? Right? If I take 1, I cannot take anything else. Is everybody following? Okay, you must keep in your mind both problems, the independent set problem and the 3 sat problem. If I take a node in a triangle, I'm not going to have anything else. So the point is, my graph, these are going to be all my nodes in the graph. The graph is not going to have any other nodes. Now what? I know that what is the largest possible independent set I can hope for in this graph? I have not shown you the whole graph, I just shown you this. And yet you can tell me what is the upper limit of my ambition here vis-a-vis independent set? Somebody said 4. Everybody sees that? Since these are lines and triangles, I can only take 1 node from here, 1 node from here, 1 node from here, 1 node from here at most, and if I'm lucky. Okay, because I have not shown you the other edges. Is everybody with me? Ask questions now. Yeah. We have, listen, I told you to keep both problems in your mind. I forgot to tell you, forget all other problems. Okay? All right? You want, the only 2 problems, 2 search problems that exist now are 3 sat and independent set. Okay? All right? So I created this, and now suddenly my graph has some order, okay? I know at least my ambition, okay? What I can go for is 4, okay? And that's what I'm going for. So this is my graph, and this is 4. My k is 4, but I have not shown you the edges, okay? There are some edges that are missing. Which edges should I draw now? Yeah? Opposite literals, right? Because basically, listen, what does it mean that I choose this node? So it means that I choose to satisfy this clause by setting x1, x2 false, right? This means that this guy is out of bounds now. That's why I draw this edge. Everybody understands that, why I draw this edge? I draw this edge to signify that if I decide to fulfill my ambition starting with the choice of x bar of this node in the first triangle, then I should not have the freedom to choose y in the second triangle, or x in the second triangle, or x in the third triangle, okay? And if I choose y, I should not be allowed to do this or this, right? And if I choose z, I should not be allowed to do this, I know, or this, okay? It was such a nice picture, but that's all right. Yeah. And so on, right? Get it? And I'm sure I'm forgetting a few. For example, x bar, and x. Okay. Right? Okay? That's my construction. Right? That's the end of the construction. What I did is for every clause I created a triangle, or in the exceptional case, a line, and then I connected contradicting literals by edges. That's all I did. Okay? And now what? And now I have to prove something. I have to prove that G has an independent set of size 4 if and only if the Boolean function B was satisfiable. And by B, I mean this guy here. Okay? You consider the x's different nodes. These are not node names. They are labels. Okay? We label them x. Okay? Okay, so thanks. These are not the names of the nodes. They're the labels of the nodes. They're what they stand for. Okay? So that we remember whom to connect with whom. If you wish, this is C1, C2, C3, D1, D2, D3, and so on, okay? Is everybody following? That's what I have to prove. Let's prove it. Usually, it's easier to go that way. Suppose that B was satisfiable. Well, it was, right? 0, 1, 1. I claim that I can pick 4 nodes here that are independent. How do I do it? Well, easy. I follow the satisfying truth assignment. It satisfies this. Why? Because why? Why? Okay? So I pick this guy. It satisfies the second one. Why does it satisfy the second one? I guess because of Z, right? So I pick this guy. Why does it satisfy the third one? Because of Z, let's say again, right? And why does it satisfy this one? Because of X. So these are the 4 nodes I pick. This, and this. Lo and behold, they are independent. Why are they independent? Because the only way in which they could not be independent is if they encoded a contradictory literal. And I could not have picked two nodes that encode a contradictory literal because I started from a satisfying truth assignment. So every literal, every variable has a value. Okay, so I avoided all edges this way. I stayed out of trouble. Why? Following a particular satisfying truth assignment. And I had no problem, I picked one. I had no problem picking one for every node, and so I achieved my goal of 4. Okay? This is how I prove that if it's satisfiable, then G has an independent set of 4. Now it's easy how everybody follow that? Now it's easy to go back and say that if G has an independent set of size 4, then there must be 1 at every triangle. And if I pick the 1, if I pick the satisfying truth assignment suggested by these 4, in this case it's going to be Y is true, Z is true, Z is true, X is false. So if I pick 0, 1, 1, then that has to be a satisfying truth assignment because it does not contain any contradictory literals because it's independent set. And 2, there is 1 in every clause. End of proof, that was it, okay? That was very sophisticated proof, okay? When it came out exactly to the day 40 years ago, people were stunned, okay? However, this guy thought of it. You know who this guy is? Who came up with this proof? Dick Karp, yeah, so your professor. Yeah, so, yeah. So everybody was stunned. I mean, how on earth did he come up with it, okay? Yeah. The what? Okay, excellent question. Yes, and the answer is why is that is in the book. We are not going to need it, okay? You know, in the book we give this reduction. Okay? Any questions? Yeah. Okay, the edges within one clause, their purpose there is to force us to take just one vertex from each triangle. Because if we could take 2 vertices from a triangle, then we could cheat, okay? And leave one clause unsatisfied, okay? And concentrate on one, skip one clause and replace from the other, okay? That's the reason. That's the intuition anyway, okay? By the way, sorry about problems 4 and 5 in the midterm, okay? You read what happened, right? I mean, so this would be a valuable life lesson to those of you who still believe that your professors are perfect, okay? I'm joking, yeah. Oh, you didn't see? Okay. There were tiny but catastrophic errors in both problems 4 and 5, okay? So don't worry. It was, everything is resolved in your favor as always. Okay, so so it has not been posted yet. I see. Okay. So if you got more points than you expected, it's because we were at fault. Okay. So all right. This will never happen again, okay? Don't worry. Okay, sorry. I thought that you had read it and you were very polite, okay? I was expecting indignation, but it was just you didn't know about it. Okay, all right. Okay. Let's go on to something more pleasant, okay? Like 3-dimensional matching. You remember 3-dimensional matching, tripartite matching? That was a fun problem where you didn't have boys and girls, but you have boys, girls, and pets, okay? And all three of them were very choosy, okay? And only a few triples were okay. Everybody understands? Everybody remembers this problem? Do you remember it? Okay, so basically you have boys, girls, and pets. And basically you know that this boy and this girl like each other, but only in conjunction with this pet, okay? So instead of having just boys and girls and lines, now you have boys, girls, and pets and triangles. Everybody gets it? That's what it is. And basically you want to find 3 triangles that cover all boys, all girls, and all pets. And here they are, okay? That's what you are trying to find. Is everybody with me? Okay? And you get to see only once the funny names for the boys, the girls, and the pets. Okay, right? Okay. All right. So let's. As you can see, I'm about to do this reduction from tripartite matching, from 3-SAT to tripartite matching. Okay. Okay, another huge challenge, all right? We want to translate the language of logic into the language of boys, girls, and pets, okay? And triangles. How do you do that? So the answer is we're going to build gadgets, okay? Gadgets. So we're going to build little communities of boys, girls, and pets that behave in particular ways, okay? All right? And then we're going to put them all together. So we're going to build a little community of boys, girls, and pets that behave like a variable, okay, a Boolean variable. What is a Boolean variable? What is its main characteristic, okay? It's a flip-flop, right? That's what it does. It's either on or off. Okay? So that's what you want to simulate. Here it is. Imagine that I have a variable x, okay? And imagine that 3 is the largest number of clauses in which x appears, or the largest number of clauses in which x bar appears. In other words, neither of them appears in more than 3 clauses, okay? So here is what is my gadget for x? It's this. Okay? I have 6 boys and girls. Here, that's my community. You have what? 6 boys. Is this what I have? No, I have 3 boys and 3 girls. Wait. So this is a boy, this a girl, this a boy, this a girl, this a boy. I have 3 boys and 3 girls, okay? Okay? And 6 pets. And I'm telling you that these 6 boys and girls, they don't like or are liked by any other boy, any other girl, and any other pet, okay? Is everybody with me? Sorry? So I'm telling you that so this is a small part of my construction, all right? It's the one that corresponds to the variable x. So I'm telling you that there is many other boys and girls and pets out there, but I'm telling you that no other boy, no other girl, and no other pet likes any of these boys or girls. There are some boys and girls that like these pets, okay, but not the boys and girls. Everybody understands what I'm doing? Exactly, yeah. For every variable x, I construct a different community of boys and girls and pets, okay? Excuse me? No. That's you know, we have no connections yet. We're just talking about one variable. And then there are going to be n variables independent, okay? In different cities, if you wish. Okay? Okay? No. There are a bunch of triangles. Basically says that the only compatible triples are these. Okay? So what I'm telling you, the only compatible triples here that you see are these. There may be some other triples that involve this pet, okay? But as far as boys and girls are concerned, that's it, okay? You're not going to see anything else. There are no extraneous triangles coming from outer space to pick them up, okay? Exactly. Each boy is only liked by 2 girls, each girl is liked by 2 boys. Okay? And my point is that if this is the situation, then what happens? Then either these triangles happen, or these triangles happen. Right? There is no third way. Since all boys must find a girl and a pet, and all girls must find a boy and a pet, the only way to do it is either take these triangles or these 3 triangles, okay? Because otherwise there will be a boy or a girl that is not matched. Is everybody following? You know, sometimes they ask me what is the hardest part about teaching, okay? The hardest part about teaching is keeping a straight face when you narrate something like this, okay? So, but I'm really good, okay? So, you know. All right, so, but I want everybody to understand this, okay? This is my gadget. This is my basic gadget. It's a flip-flop, all right? Why is it a flip-flop? Because it models a variable. It's going to be the 3-dimensional matching gadget for a variable. All right? And why does it flip and flop? Because if, as I'm promising you, there will never be another boy or girl who likes one of these 6 boys and girls, then the only way that I can have a matching is if the cross-hatched, lined triangles are taken, or the gray line, the white triangles are taken. The shaded triangles. Okay? And so, I say shaded is true. Okay? If the hatched triangles are taken, then it's false. If the shaded ones are taken, it's true. It's a flip-flop. Do you have any questions? Ask them now. Yeah. So the 3-dimensional matching, you must pick a bunch of triangles that eventually will have to cover all boys, all girls, and all pets. Okay? If every boy here is liked by 2 girls alone, you have to take either this triangle or this triangle. And if you take this triangle, you cannot take this triangle because this boy is taken. So you have to take this triangle because this girl cannot do anything else. And you cannot take this triangle, but you have to take this triangle. Okay, so that's... No. We are creating the instance now. We are going to reduce from satisfiability to three-dimensional matching. And I'm telling you what kind of easiness I'm going to give you. In the end of the day, you are going to give me a formula, and I have to create to you a bunch of triangles. And I'm just telling you my plan now. How it's going to be, how it's going to look like. And so I'm telling you, for every variable, I'm going to have one of these guys. And it looks good. Why? Because it behaves like a variable. It flip-flops. Exactly, yes, true. But my three-dimensional matching problems that I'm going to construct in my reduction, okay, on my lecture, okay, right, is going to be like that. Have a problem with that? You don't have to. You are not reducing the general 3D problem. You're reducing to the general 3D problem. No. You want to show that the three-dimensional matching problem is hard. So we are going to take a Boolean formula. This is, by the way, this is an extremely productive conversation, okay? Yeah. So you are going to take a Boolean formula and create out of that a three-dimensional matching. This is going to establish that three-dimensional matching is hard, okay? Of course, it establishes that three-dimensional matching that looks like that is hard. But if you cannot solve that, how can you solve three-dimensional matching in general? That's a special, yeah. In other words, this is revealing something extremely important. That if you prove a special case of a problem hard, you have proved the problem hard. Okay? If you have proved that a special case of a problem is hard, then the whole problem is hard. Yes. Right. So if the tree is hard, but if the tree is hard, okay, if the empty graph is hard, then you are in trouble. Then everything will be hard. No. It's of always. If a special case of a problem is hard, then the problem is hard. Any special case, yes. So the point is, okay, you are used from the following pattern, that if a special case of a problem is easy, it doesn't mean that the problem is easy. That's true. But if a special case of a problem is hard, then the problem is hard. Because there is always a reduction from the, you understand? Because there is always a reduction from the special case to the general case. Just do nothing. Embed it. Okay? These are reductions that are fun, and frankly, they're the most useful. Yeah. A specific number of? Oh, I see. Three. Because I assumed that this variable appears at most 3 times unnegated and at most 3 times negated. So these guys here, these pets here are going to be appearances of the variable. Okay? These are going to be let's see. These are going to be the true ones, and these are going to be the false ones. The negated, and these are the unnegated. Okay? We'll see how it goes. Yeah. Yeah. No, because if the special case of a problem is hard. In other words, okay. Imagine, okay. Suppose you are trying to prove that solving 6th-degree equation is impossible. Okay. Suppose that you can only prove it for the special case where the first coefficient is 0. In other words, you have a 5th-degree equation. Then you prove it for in general, right? Because if you cannot solve fifth-degree equations, how can you hope to solve sixth-degree equations? That's what you are seeing here. Okay? If the special case is impossible, of course the general case is impossible. The general case is always harder because you have to face other patterns. Do that make sense? Yes, sir. I didn't know it before, but I will know it once I know that I can reduce satisfiability to it. It could be 1% of all. But the point is that if your job is to write a program for the general case, certainly somebody could give you the 1%. And if you cannot solve this 1%, you cannot solve the problem. Right? Make sense? No, but I mean, no, but solving a problem, writing a program to solve the problem means that you should be ready for any case. That's true. That's true. Yes. I mean, and in many problems, it turns out that you can write a program that solves most problems. Okay, but you know, sometimes it happens that the interesting cases are the ones you cannot. You know what I'm saying? Because the ones that you can, people just eyeball them and they never send them to you to solve. You know what I'm saying? Yeah. Say it again. So I'm going to be given a Boolean formula, and I'm going to construct a bunch of triangles. Okay? And the triangles are going to behave exactly as the Boolean formula. Yes?
So why, for every vertex in the, for every boy, for instance, in the gadget, you're only connected to two girls.
Right.
That's for the other two variables.
You are connected, you know, basically what I want to achieve is this flip-flop effect. That the only way that this can be part of a good solution, of a solvable problem, is either to take the three triangles or the other three. Flip or flop. Okay, that's what I'm trying to achieve. More questions? Yeah. Yes, they have a name. I'm not writing it on the blackboard. Yes. No. X lives in a different space. Okay. All these things, in my mind, I think of X as X. Okay. So the bottom line is that I do this for every single variable. If my formula has 100 variables, I'll do 100 of these. Okay. And now the only question is, what is clause? Okay. What do I do about my clauses? Okay. So imagine that I have a clause here, which is, I don't know, X bar or Y or Z bar. All right? Okay. So here's what I'm going to do. I'm going to have one boy and one girl. Let's call it boy sub C and girl sub C. These are the boys and girls of this clause, okay? And they like each other. The question is, which pets do they like? And it turns out that they like this pet. Why do they like this pet? Because this pet will be available only if X is false. You see, if X is false, then the hatched triangle is going to be taken, and then this pet will be available. Okay? And they also like another pet, which is in the hatched of the Y, right? Why? Because if y is true, then this pet will be available. And these guys will equally satisfy. And then I'm going to have another one at the z thing, okay? Remember that for every variable, I have a community like this. And these guys are going to pick one, the right one, from each community. The right kind from each community of x, y, and z. And that's the result. These guys can't be happy only if one of the following three things happens. Either x, in the x gadget, the hatched triangles get together, in which case this means that x is false. Yeah, that should be right, that's right. Or if in the y community, the what am I talking about here? The shaded triangles are picked. In which case, this hatched pet will be 3. Or, third case, if none of these two works, there is a last chance. If in the z variable, the hatched triangles are picked, which means that z is false, and therefore b sub g and g sub c deserve happiness in this case, right? Because their clause was the clause C was satisfied. Okay. So, what's the bottom line? The bottom line is this. This is the whole thing. Okay. There is a last detail that I will only reveal if somebody asks. Okay. But that's it. All right. That's essentially it. That's the heart of the construction. And what happens? Basically, we are reducing from satisfiability to a really strange problem, okay? Three-dimensional matching, three-partite matching. What do we do? For every variable, we create this strange community of boys, girls, and pets. The pets are available in the beginning. Once we decide which of the three triangles are going to fit, only 3 of them are going to be available. These are going to be available, have the same semantics, okay, that x is true or x is false. The same is for y and z, okay? So the only way for this huge mess of triangles to have a you are annoying. Yeah. If the only way that you can have these triangles, this mess of triangles have a solution, in other words, have a way to satisfy all boys, all girls, and all pets, would be for every variable to pick either the hatched or the shaded triangles, all of them, and do it in such a way that every clause can be satisfied. And that would mean that the overall formula would be satisfied then, because every clause is satisfied. Okay? Yeah?
Suppose in your satisfied clause, all 3 variables are true.
Okay. I was afraid of that. Somebody would ask this. Okay, sure. Okay. So here's what he's saying, all right? That this way, some pets will be exposed in the end, right? Because there are 3, suppose that all 3 are true. That's allowed. If all 3 are true, I'll pick one. What happens to the other 2? Okay? The point is that we know how many of them there are going to be. Okay? How many? It is, let's say, imagine that all of them are 3. It is 3 times the number of variables minus the number of clauses, right? So that many of them are left out in the code. What do we do? Easy, okay? Anybody can think what we do? How do we fix this? We create that many couples who are generic animal lovers, okay? They love all pets. And so in the end, they just pick up the pets that are left out in the code. Okay? But that's a detail. Forget about that. I mean, the main thing is this, that in order to reduce satisfiability to another problem like three-dimensional matching, which is not logical, it's not about logic and Boolean functions and variables at all, what you have to do is you have to create gadgets, okay? The gadgets basically play sort of, there should be structures within the domain of the new problem, of the problem we're reducing to, which behave like variables. And how do variables behave? Have a very simple behavior, the flip-flop. That's why we did this. Okay? And then you must have another gadget which basically does what clauses do. What do clauses do? They constrain, okay? They basically tell you, you have to be like that. They chose, the truth assignment you chose has to satisfy one of these three literals, please, okay? And we do it this way. These are a boy and a girl who only like three pets. The three literals in the clause. And if one of them is available, they're happy. But this means that the clause was satisfied. And in that, we do another pass to fix all mistakes, okay? All pets that nobody picked up. That's the proof. Of course, now, we have to prove that what? There is a truth assignment that satisfies all clauses of B, if and only if there is a set of triangles that covers every boy, every girl, and every pet. But it's easy now. Why? Because if there is a satisfying truth assignment, we flip or flop the corresponding community from each variable the way dictated by the truth assignment. And then we satisfy the clause couples through a pet which is available. Why? Because one of the corresponding variables must have the right value. Why? Because we started from a satisfying truth assignment. And in the end, we pick up the remaining pets in some other way. So that's the proof that if there is a satisfying truth assignment, then there is a complete matching, a complete three-dimensional matching. And the other way around. If there is a complete dimensional matching, then every variable gadget must be like this, every clause gadget must be satisfied, and therefore there is a satisfying truth assignment. So I know it's a very sophisticated, tough way of looking at problems, okay? But it's new, very new. But this is the only thing, the only way we know to get substantial, irrefutable evidence that problems are hard, okay? That's why it's a valuable thing to learn, all right? So see you next time.